That's not so nice for the photo. Okay. After a short introduction, I will go immediately to the micropolar plates and shells and the governing equations. After that, I discuss something about the elements of the gradient elasticity, and finally, this through the thickness integration procedure and micropolar plates. My part number 5 are the constitutive equation of the gradient theory of micropolar shells, and some. Victor, this works here or not? What I have to do here?
You have to click on the first.
You have to back.
First one. Click on it.
The first one.
The introduction.
Introduction. What?
Yes.
Here. Maybe it's better to make from here. It's page down. Yeah. Okay. Last part will be the conclusion. Let's start with introduction. What is the most important thing here? Our main goal is to discuss the constitutive equation of plate and shell theories. And today I want to focus your attention that we try to understand how it is related to the second derivatives of the translation and the rotation fields, so in this sense, like a gradient theory. Our motivation is coming from this 3D gradient elasticity, and there are some applications, for example, given in the papers of Ru-Alfantis, Asris, Forrest, Goodkin, De Lissola, Mojon, Neff, and Steinmetz, and so on and so on. There are more people in this field. And the second motivation is coming that there were some discussion, for example, given by Reddy, that the third order and higher order theories of plates and shells can be also interpreted as a case of a 2D gradient series. What is the main effect which we can observe in this theory? If we make, for example, the diameter of the sample smaller and smaller, then we observe in the experiments that we have increasing, for example, moduli. For here in this case, it is the Young's moduli. And you see by the dotted lines, this will be the classical solution. And the red line, this is some fitted results. There are no clear theory in the background, but this is coming from the experiments. We have such more experiments. Here are given the same picture which is shown in the presentation of Victor. But last but not least, there are other researchers in this field, and you see here, it can be sometimes that the moduli are increasing, and sometimes it can be happens that they are decreasing. So it is not only one tendency that it must be stiffer and stiffer, it can be happens vice versa. Let's now switch to the series of plates and shells from the point of view of generalized continuum models. Second gradient type series are given, for example, by such type of equations. We have homogenizations. We have to include the micropolar type kinematics. That means rotations and moments as a kinetics should be absolutely independent. We have additional degrees of freedom, for example, such things like warping functions, and sometimes we have also dependencies of curvatures. There are different approaches in this field. One is the so-called direct approach, discussed first time in a close manner in a monograph which were published more than 100 years ago by the brothers of Kossora. And you see the Renaissance starts only after 50 years in the first paper of Ericsson and Truesdale in this field. And there are a lot of other contributions, not only in the Western world, but also in the Eastern world. In my university, there were Gilin and Palmov. There's a monograph of Rubin discussing all these things, 3D, direct approach, 2D, 1D. So different approaches are suggested here, but always this so-called direct approach. A second idea is to start with a 3D continuum and then make a reduction. That means we get two-dimensional equations, but the starting point is the three-dimensional world. Such papers were presented by Ehringen, But you can see also this approach in the papers of Heisler and other people which are presented here. And last but not least, if we have all these properties independent, that means the rotation and translations, and this is also a natural way to start with a so-called general six-parametric nonlinear shell theory. One of the pioneering papers or monographs in this field is the monograph of Levi and Simmons, and there is a Polish school, mostly known from the Gdansk area. Petraszkiewicz, I think, was the first who presents these theories. And now let's discuss the basic equations or the governing equation of such type of theory. You see here, if we have a direct approach, then we have only a deformable surface. And then we can start, as usual in continuum mechanics, to formulate the balances. I want to limit my discussion only to mechanical fields, and so we have a balance of momentum and the balance of moment of momentum given here. This is like in the first year of education of any engineering students in the base course of engineering mechanics. Here is the local form instead of the integral form, which was on the previous slide. And you see here the tensors T and M. That means the force tensor and the coupled tensors are given in a more general form than in the classical theory, for example, in the Kirchhoff or Love type theories. These are the representation in Cartesian coordinates. And finally, we have to introduce static and kinematic boundary or also mixed boundary conditions as shown here. For the strains, we can introduce so-called strain measures. Examples are given in the first line here. So we have something like the deformation in plane and out of plane. That means curvatures by kappa, and the in plane by these epsilon value are given. Instead of the three-dimensional unit tensor, we have now a two-dimensional type, which is given here. And last but not least, we can introduce these strain measures as work conjugated properties to the stress measures, and we can formulate the principle of virtual work. The last task in this field is the formulation of constitutive equations. Let us assume that we have an isotropic shell, and then in this case we have such type of strain energy density. You see here we have 8 elements in the equation 10, and you can see there are contributions again which are related to the energy properties, in plane properties, and the other are out of plane properties. The problem is now to discuss these parameters alpha and beta, because these are constitutive parameters, and you see immediately from here that there are more than in the classical case, so more duties with the estimation or identification of these parameters. The T and the M tensor are given in the classical manner, like derivatives of the energy by the strain measures, as shown in equation 11 and 12. And last but not least, there are some estimates. You see here the limits of the constraints for these constitutive parameters. You can find these discussion in our publication, but also there is a nice paper in the Sum journal, if I remember correct, by Patrice Neff. He discussed also these properties. And in the Polish group of Koszalewski and the others, they were given some identification of these parameters. What you see here, some of the parameters are really equivalent to 0, but the other parameters should be handled a little bit more careful. Alpha 1, alpha 3, and beta 1 and beta 3, they are like in the classical theory, because you have seen here there is the in-plane stiffness C and the bending stiffness D, like in the classical case. The exception is alpha 4 and beta 4 properties, because now we have the influence of 2 additional dimensional coefficients. So one of these is well known as a shear correction parameter, but in this case it is not a shear correction, it is related to some type of behavior. And you see here alpha S, this is similar to the shear correction in the classical or non-classical theories, and alpha T is related to the torsional behavior. For alpha S we have some well-known estimates, for example this p square over 12 or 5 over 6. You can introduce also other parameters. It depends on the geometry of the cross-section, etc., etc. Alpha T, there is only one estimate known which was presented in the paper of Petashkevich. Let's switch now to the elements of the gradient elasticity. There's only one slide. You see here the main or the basic equations for the gradient elasticity. It starts maybe in the 1960 with this idea to introduce for the strain energy not only the first gradient of the displacement but also higher gradients. It is clear if you have more gradients then you have a more accurate description of the reality, and the finite number will be much better, and the infinite number is the best case, but then you have trouble again with the identification of the constitutive equations. The realization of this procedure, for example, in the paper of Ehringen or Ru-Alfantis, you see here these ideas, how to discuss or to handle these constitutive equations. And what is interesting, in both cases you have a parameter L square, which is something like an internal length parameter. And if you introduce these parameters, you can introduce higher gradients. In the first case, this is a higher gradient of the stress. In the second case, you have a higher gradient for the strains. And finally, this has some influence on the constitutive equation, as shown, for example, here by this equation 18. Now we try to apply these things to the micropolar plates, and we use this through the thickness integration procedure. So let's show it at first. For the classical elasticity, you have the equations for the equilibrium state, for the boundary conditions, and for the energy relation, and then you get the stress results for the 2D equilibrium equations as shown in the lower part of the slide. The brackets, that means integration over the thickness, and you can introduce independence on new simplified parts for the plate equation. In this case, there's no influence of the curvature, but you can use also similar relations for the case of shells. If we have the gradient elasticity, then again we take the same procedure. We start with the basic equations for the 3D case. We have some additional terms, which is clear. And then we get the stress resultants and the 2D equilibrium as shown by the last equations here on this slide. And now you have more equation, more influence factors, a little bit more complicated structure, but if you assume this is correct, then this is an automatic procedure which is coming from the previous slide, and it is correct in this. The constitutive equations in this case, again, a little bit more complicated, because now we have not only the standard terms with this alpha 1, alpha 2, and the beta 1, 2, and so on, but we have also the influence of this internal length scale factor, which is shown here. And last but not least, you can again show that such type of theories we can formulate in the sense of the Ru-Alfantis theory. This is in the first part of this slide, and you can also introduce such types of equation in the Ehringen sense. So in the first case there were higher gradients for the strains, in the second case higher gradients for the stresses, and so you have the influence on the right hand side in the constitutive equations, or you have an additional part for the left hand side in the constitutive equations. Last but not least, let's have a look briefly on an example. Let's discuss the problem of the bending of the square plate under constant transverse load. The basic equations are given here. And finally, we have now different types of final equations. We know there are the standard form of the Kirchhoff plate theory. This is what's this first part, for example, of this equation. And now, in addition, we have additional elements. If we have a no gradient theory, but of micropolar type, that means the scale factor is equal to 0, then we have only this additional contribution, which is related to the non-classical part. This is a classical bending stiffness, but you have here the additional influence from the shear, which is presented by this element. If we have this Ru-Alfantis type gradient theory, in this case, the modification will be on the left-hand side of this equation, because we have an influence on the strains, and so it must be some changes on the left-hand side of this equation, which is presented here. For the Ehringen type, we have the influence for the stress part, and so it is clear now there are the changes on the right-hand side, and so we have two types of equations. Let's make some final conclusions. At first, the gradient theory of micropolar plates and shells was discussed. We have used the Ru-Alfantis theorem, and we discussed a special type of constitutive equation. Today we limit this equation to the pure mechanical behavior and the isotropic behavior, but you can extend it as you like it in any directions. And we have compared the two types of the basic equations, the so-called, in our sense, Ehringen type 2D equation and Ru-Alfantis type 2D equations. What we can do maybe in the future, we can try to understand what happens if we have something like a general gradient nonlinear theory of micropolar shells. The problem is not the nonlinearity. This is a general problem in the shell theory, but not in this case. The question is, what will be if we change at the same time both parts, the strain part and the stress part? And we can follow this paper of Jeremejew and Petashkevich, and we try to develop the theory of material symmetry groups of second order of micropolar shells, and we can construct the reduced constitutive equation for some anisotropic cases. We know the isotropic behavior is very important for the classical materials, but if you want to switch to some advanced materials, in this case it is necessary to include the anisotropy, but as usual you have some special cases, and we want to check what happens for these special cases. And last but not least, when we switch out the pure mechanical behavior and we are going to other fields, then the first attempt will be in the case of the influence of thermal factors, and so we have to develop also a theory with respect to thermodynamics. Thank you for your attention. This is for today. If you are interested in some further literature, I can present it.
Nice talk. Can you give us the motivation why you want to do further higher gradients apart from the Kosovo micropolar ones? Do you have, for example, experiments which would suggest that you need another length scale?
Yeah. At present, we have not checked the literature with the same, because we have no own experiments, and we have not I have not very carefully checked the literature with respect to this. The basic idea was that we have seen that there is again a so-called didactic project in the background, the didactic idea, and you can very easily make formulations this direction, in that direction, or the third direction. It is a little bit similar to your lecture today. You have also present some didactic concept and then apply it to different, because this Hanke method is also very known, but you have shown that there is something in the background and you can use it in this direction, in that direction. And this was our basic idea at the present or at the moment.
All of these theories
see, in the simplest case, we have some solutions. This is not the problem. We discussed these things several times, also with respect to the higher order plate series or shell series, because you have also after, so say, Kirchhoff, then Reisner, after that you have some trouble. But you know that, for example, Reddy have built up the third order theory, other people have higher order theory, and there are some, I will name theoretical approaches to formulate something. How close it is to the engineering problems is another story. And sometimes I'm also afraid that from the engineering point of view, you will have no so clear boundary condition like in civil engineering at the very beginning. So there will be maybe trouble.
Yes?
Do you expect very different solutions from the Altenbach approach or from the Ehring approach? Primarily the operator is one time on the left-hand side and one on the right-hand side. Probably the difference is not that much.
There's different boundaries.
There is simple example of supported, let's say, quadratic plane. There is a difference. It depends also for a different loading. Depends on type of loading, because it looks like order of differential equations are different. So you can assume some boundary solutions somewhere.
I would just like to make a comment on the question of boundary conditions in these higher order theories. Of course, you have always the possibility to just do nothing, which means Neumann boundary conditions for the higher gradients. If you prescribe something specific, that would lead to a boundary layer effect, which you pass from one. That is boundary layer theory. But if you just are interested in the internal rearrangement of whatever in the material, you just leave the boundary conditions open. So that would be my point. Open. I mean open. You just do nothing. You do Neumann. Yeah, you don't prescribe initially type boundary conditions.
That's what the mission is. It needs work. It needs work.
Follow up on the question that was for plane theory, is a very specific.
Sorry, tell me
The high order theory of geometrical type.
You suggest to use a variation principle, and then you have some automatically,
Yeah. And gradient theory has that indicated and one.
Okay, so I think all the speakers